This is CE 3102 Tutorial 5B question 1. In this question, we're given a LTI system that has the impulse response of this. Notice the arrow here, it indicates that n equals to 0, so it should be lining up to 1. Well, we are now asked to find the Z-transform of this impulse response, sketch the pole and zero diagram with the region of convergence, find the B and A coefficients, and then discuss the meaning of B and A. Let's see my answer. First, I will sketch for you what is an LTI system and where does Hn comes out. This box represents the LTI system. Hn will typically write here to denote that this is the impulse response of this system. So by an impulse basically means at time 0 you send an impulse. Delta n is this symbol where the magnitude is 1 at time n equals to 0, and this is n. And what will come out of this is this sequence. So before time n, all the value is 0 because we're assuming that the system is causal and relaxed. Causal means that only when the impulse comes do we have the output. Relaxed means that before the input comes, there is nothing. The value of the output is 0. Right. The first value is 1. The second value is 2. The third value is 1.25. The fourth value and the rest are all 0. So this is h of n. Remember that this is a discrete time system, therefore the input only happens in discrete time index of 0, 1, 2 and so on. So this diagram tells you how to draw this impulse response. You should draw an impulse as the input, the LTI system as a block, and the output is this sequence, which is represented by this set of values in this curly bracket here. Remember that this arrow here will tell us the time n equals to 0. So showing us that the first value, this guy, is exactly this yellow here. We now want to transform this Hn into Hc. So this is the Z-transform of the impulse response. We remember the equation for the Z-transform. Basically, we plug in the sequence here, and it is from negative infinity to infinity, multiplied by this sequence with z minus n. So because the sequence is causal, this guy actually reduces to 0 because there's no values before them. And all we are doing is to plug in all these values here for different n's. And this is what we get below. So since we have only 3 values that are non-zero at n equals to 0, 1, 2, so this is n equals to 0, n equals to 1, and n equals to 2. The minus sign came from the Z-transform. We plug in the values here. So Z-transform of a finite sequence is very simple. You take the sequence and you expand it into a polynomial of negative powers of z, and the index here refers to the index. So actually this is a lossless transform because all the values of the original sequence are already there, and the index tells us where is the actual original value in the sequence. Sometimes we do not we want to convert this into B's and A's, where B's and A's are the coefficients of the filter in MATLAB. Now in MATLAB, B represents the numerator of a filter rational function, and B is in the negative power in this descending order. So what we do is that the first one goes to here, the number 2, let's change the color, number 2 from here goes to here, the number third values goes to here. Okay, and a equals to 1 because in the transfer function there is no a coefficients and there is only 1 here. So remember that h of z is y over z divided by x of z, and if you write the equation of h of z, you only get the b's coefficients and the a coefficients is 1, simply because our output has no feedback. Now we want to find the pole and zero. What do? Well, we take the h of z, and remember that currently my h of z is in the negative powers of z, which is not in an appropriate form. So we multiply the top and bottom by z square to convert these negative powers of z into positive powers of z. So we have the original sequence, and below we have z square. And we want to factor this out now so that we can have the poles and the zeros of h of z. So basically we take the numerator polynomial and factor it out. So z plus 1 plus j half, z plus 1 minus j half, these two are the factors of this second degree polynomial. And what about z squared? Z squared can be broken down into z times z, which is z squared. Now, so we now draw the poles and the zeros. Where are the poles? The poles are the value where this denominator becomes 0. So the denominator becomes 0 when z is 0. So this is when z is 0. And we draw a cross here, and we have 2 because we have 2 poles. What about z plus 1 plus j half? So this means z is equals to, when z equals to minus 1 minus j half, then the numerator becomes 0. So where is minus 1 minus j half? So what you do is that you draw the real plane and the imaginary plane, and then you draw a unit circle. So a unit circle means a circle of radius 1. And then this, along the real line, this is 1, this is j, this is minus 1, and this is minus j. So this is a circle of radius 1. We call it the unit circle. And now we have to put z equals to minus half minus j half. Sorry, minus 1 minus j half. So you move to minus 1 here and minus j half. So this is the 0 of one of the factor in the numerator. The other guy is z equals to minus 1 plus j half, so which is this guy over here. So when z equals to minus 1 plus j half, this guy goes to 0. And with it, so we go to minus 1 plus j half. So this is j half over here. So these two are the 0. So we draw a circle, a 0 here for the zeros of the numerator. And now you want to draw the region of convergence. The region of convergence is actually the external region, because this is a causal filter, to the pole. So in this case, the pole is at the origin. So in fact, when we draw, we should draw everything outside this pole, and in fact it covers everything except at the point when z equals to 0. So here I explain question 1a. Thank you.